pulse. This can okay.
They kind of rotating neutron stars with.
Yes, that is what means. If I ask what are they? So they are not main sequence star like sun, right? They are actually neutron star. So now if I ask you the question, what are neutron stars? So means I will not derive anything because pulsar science itself can be a say few lectures. So I will just give an introduction to a few aspects and then you can go through the slides, read and later ask me or email me. So here you probably know about evolution of stars. So okay, here this is some schematic diagram. So if you have a normal star, say like our sun is very normal star. So after some times it means at the end of its evolution it will become a giant, red giant. And then ultimately it will become a white dwarf. I will explain what is a white dwarf later. And if say you have a star which is say 20 times more massive than sun, what will happen? So it will also become giant, but it will be much bigger than what sun will become. So sun-like stars, when they become giant, we call them red giant. And more massive star, we call them red supergiant because they are super big. And when they die, they go through explosions, supernova explosion. And then they become either neutron star or black hole. So say if the mass of the sun is mass of the star is between 10 times sun to say 30 times sun, it will become a neutron star. And if more massive, say you have a star 100 solar mass, it will eventually become a black hole. And when I say black hole, I actually mean scalar mass black hole. Because there are different types of black hole, like scalar mass black hole, it will be 10 to 30 solar mass. Say you have 100 solar mass sun. And its core will collapse to a say 10 solar mass black hole, and the outside material, they will explode and there will be ejected material. But there are other types of black holes like primordial tiny black holes. There can be supermassive black hole which you have in the center of every galaxy. Now the concept of is why when they stars die, why they become white dwarf or neutron star. Let us try to understand the physics little bit. So we know when you have a burning star like sun or any massive star, there is nuclear fusion going on, right? First you have hydrogen gas, then hydrogen fuse to helium, helium can fuse to carbon, carbon give you oxygen, oxygen can give silicon, silicon can give to iron, and it becomes this shell-like structure because center of the star is hotter, so evolution becomes there faster. So you might have a time where center has iron, then silicon core, then oxygen layer, then carbon, then helium, then hydrogen. So this is like onion-like shell-like structure. But iron is very stable. So in normal situation, you don't get elements heavier than iron. So how we get all these heavy elements? That will come later. Now see, we need to understand two things. This, say you have a star which is as massive as sun, or say I am saying 10 solar mass or 100 solar mass. So they are also strongly gravitating, right? So we all, gravity, any two particles are attracting each other, right? So if I spread my hand, my fingertip is getting attracted to my solid, but it is not collapsing because we have bone structure. Like Earth also is not collapsing because Earth is solid, it has structure. But what about that gaseous cloud, means sun or stars? Why they are not collapsing? Means as one atom at the surface is being attracted to the center, right? Why it is not? Because gas pressure, right? So we all, just a minute, we all know that ideal gas rule, right? PV is getting, and as they burn, you have a burning star, so very high temperature, right? So T is very high, pressure is also very high. So gravity is acting inward, and this gas pressure is acting outward. So they balance, and that is how all these mencicle stars exist. Now, as I said, that iron is very stable. After that, no nuclear fusion is possible. So say you have finished with your nuclear fusion, so no more heat is being generated, but the star is radiating heat, right? So it starts to cool down. So when it cools down, pressure decreases. So there will, one time will come when gravity wins, right? The star will start collapsing. And what happens is, star, you can say that it is in the atomic plasma. So star is collapsing, you are bringing all the atoms close together. But can you say like 100 solar mass stars? So gravity is too high. But at least you cannot bring two atoms in the same place, right? Because we know atomic structure. There is nucleus and orbital electron. So there is a finite size of the atom. You cannot bring two atoms closer than that. But if gravity is too high, it tries to squeeze that. So in that case, what happens? That atomic structure breaks. So that atomic electron orbits, they break, and they become free electron. So then, when you have atomic structure, two electrons cannot come close together, right? But if it is free electron gas, free from atomic bond, they can come close together. And you have two small nucleus, so you can bring nucleus close together. Right? So what you have means, under gravity, atoms breaks. You have free electrons and free positively charged nucleus. But can you bring them? So electrons, you can bring them very close. But can you put them to exactly means at the same location of space? You cannot, right? And also in quantum mechanics, probably you have read about Pauli exclusion. And all these electrons, proton, neutrons, they are Fermion, right? They will obey Pauli exclusion principle. Means all quantum numbers cannot be same. So you cannot bring them exactly at the same place, because that would need all quantum numbers to be same. So it will give means the free Fermion gas, it will give a pressure against squeezing. So that is called degeneracy pressure. So probably if you studied statistical mechanics or from Landau-Lifshitz, you have heard of degeneracy pressure. I am not going into details, but what is the expression? Means it obeys that Fermi-Dirac statistics. So I said under gravity, you have a white dwarf. Yeah. So I am now going to explain white dwarf. So you had a main sequence star which died, means no nuclear fusion. Under gravity, it collapsed. Atomic structure broke. You have free nuclei and electron gas. But gravity is still trying to collapse. After some time, because when it comes very close together, degeneracy pressure will go in. So there will be a balance state. Means electron degeneracy pressure will balance further collapse of gravity. So that stable structure is known as white dwarf. And why white? Because if you plot in the their mass and bright colored diagram, HR diagram, they look white. So that is why they call white. And white dwarf, because after squeezing, they are already small. I will compare their size soon. So those are white dwarf.
After collapsing the atomic structure?
Yeah, so under gravity, atomic structure collapse. You have free electrons and free nuclei. And then this free electron, that is a electron fermion gas, right? Because electrons are fermion. So they have degeneracy pressure. So when this degeneracy pressure is equal to gravitational pressure, you get a stable structure, means no more collapse. So you get a stable stellar structure. So those stable stellar structures are known as white dwarf. Now if your star was even more massive, so gravity would be even higher, right? And it might happen that this degeneracy pressure of electron gas, they cannot balance gravity. What will happen? So now you have electron gas and nuclei. Nuclei have protons and neutrons, right? But if gravity is too strong, means if you study nuclear physics, means like in atoms we have atomic electron orbital level. Inside nucleus also means electron protons, because they are also fermions, right? They are, all the quantum numbers cannot be same. So they are also separated. So under gravity, means you cannot squeeze nuclei. So if gravity is too high, even nuclei would break. So you already had free electron gap. Now your nuclei, all the nuclei you have, they also broke. So you have free protons, free neutrons. Now when you had atoms, that time electrons were supposed to be in the orbits. They could not come to the nucleus. Now you have free proton, free neutron and free electron. So proton and electron means Coulomb force, they will attract each other and protons will absorb neutrons and protons will convert to neutrons. Right? So you have mostly neutron, which means in your matter you have mostly free neutrons. So again, neutrons are fermions. So they will also give degeneracy pressure because they follow Fermi exclusion principle. So if means the mass is so that this neutron degeneracy pressure can balance gravitational collapse, you will again get stable structure, right? No more collapse. So if that happens, the stable star you get, that is neutron star. And if your gravity was even higher, means even neutron degeneracy pressure could not stop the gravitational collapse, you get black holes, nothing else. So that is the basic concept. So any question up to this? Okay.
Neutron degeneracy pressure is higher than the electron degeneracy pressure.
Yes. So
when in the first stage when white dwarfs are collapsed, the mass is too low, that time both the pressures will be acting. Neutron degeneracy.
No, that time you don't have free neutrons, right? You have nuclei. Okay. So you need to break nuclei. You need more gravity to break nuclei. Okay, now,
ma'am, why, like, we can understand that neutron degeneracy pressure will be higher than electron degeneracy pressure, but why should it be so?
Okay, so that we need to do the calculation, because do you have any idea what is the mass of a neutron? So neutron mass is much higher than electron mass, right? Electron is and electron is 0.5. So because of that, your chemical potential is low. So chemical potential comes in the Fermi statistics. Okay, now.
What if the degeneracy pressure was like exactly equal, the mass was such that it was exactly equal to the inward gravity, then what will happen?
Mass was so that
if the degeneracy pressure is more, we get a white dwarf. But if it's not, as in if it crosses the limit, then we get a black hole. What if the
okay, so first your star starts to collapse. At the point degeneracy pressure is balancing gravity, you get white dwarf. When neutron degeneracy pressure is balancing gravity, you get neutron star. When nothing is balancing, means gravity wins, you get black hole. So which condition you want to be?
okay, I think I understand.
Yeah. Okay. So now this white dwarf and neutron stars together we call compact star or compact object. Why we call them compact? So that will be clear from this table. So say I have a white dwarf of 1 solar mass. So its radius means from your model of electron degeneracy pressure you can calculate. And actually, you will need some modification because there will be little bit atmosphere, because little bit hydrogen, because everything was not fused, right? So theory and observation both said if you have a 1 solar mass white dwarf, its radius will be around, means it might, also all these calculations we did not consider the effect of magnetic field. So if you consider magnetic field, that will come to your equation and it will change mass radius little bit. So, but anyway, 1 solar mass white dwarf, WD, so that radius is 7 into 10 to the power 3 kilometer, and radius of sun is 7 into 10 to the power 5 kilometers. So same mass, but sun's radius is 100 times larger. So you can understand, means the average density of white dwarfs is much higher than sun. And if you consider neutron star, same mass neutron star can be little more massive also, but its radius will be more or less 10 kilometers. So you can understand, means how dense neutron star is. So there is, means sometimes we say if you can take 1 spoon of neutron star matter, its weight will be heavier than right? So that is why we call them compact also. So there is something called compactness parameter. So this is just to compare them with black hole. So for black hole, you know, means for black hole you do GR calculation, right? So if for black hole, means if you don't consider spin, then GR predicts that mass of a black hole will be satisfy this relation. Means this G is gravitational constant, C is speed of light, in fact M is mass. So if you calculate dimensionally, you get the unit of length, and this is called Schwarzschild. So 1 solar mass black hole Schwarzschild radius is 2.95. For neutron star, its radius is 10, and for white dwarf 7 into 10 to the power 3. And so half means there is another parameter RG, gravitational radius. What is for black hole? It is half Schwarzschild radius. So it is just the Gm by c square. So for white dwarf and neutron star, it is all same, right? This parameter Rg is just mass comes, and I have taken same mass, so Rg is same. And the compactness parameter is defined as Rg by R. You can say M by R, but that would not be dimensionless, right? It is better to have some dimension quantity. So this is basically M by R, but G and C square just to make dimensionless. And that you can compare. For black hole, it is 0.5 because this is R and this is Rg. 0.15 for neutron star and 0.302 for white dwarf. So few things to, I think someone said that neutron stars are rotating, right? But everything is rotating, right? Earth is also rotating, sun is also rotating, neutron stars are rotating, black holes are rotating. So, you know, spin period of sun, it is around 25 days. Spin period of white dwarfs can have different range, 0.01 day to few days, 4 days. But neutron stars can actually spin very fast. Means their spin period can be in the order of millisecond to few seconds. So just you have a neutron star which is say 1 solar mass, or sometimes you have even 2 solar mass neutron star, and that is spinning. This one spin is completing within a millisecond. So they are so rapid. And also neutron star is very highly magnetized. I will show some diagrams. Neutron star magnetic field means we don't know. For sun is close, we can do different types of study and more simulation. But for neutron star, we exactly don't know about interior. So that is an open problem to work on understanding interior of neutron star.
Ma'am, the spin period of black hole is greater than that of neutron star.
In black hole, just we don't know. Yeah, so for black holes, we don't know because we are not seeing anything for a black hole, but there is some theoretical limit that mass by angular momentum ratio that
Like train should.
that trend should follow, but there is an upper limit beyond which it cannot go.
Why the
But sir,
period of neutron star is a challenge?
Yes, because one by one, because we don't, whatever we see means I will say that emission we see, those are coming mostly from magnetosphere. So we can probe neutron star magnetosphere, and then we try to find indirect way to know means what is there inside. Yeah, you have something. Okay.
What is the origin of this strong magnetic field for the neutron star?
Okay, so one thing you can actually ask that why neutrons are charged neutron, but still they have a magnetic moment. We call nuclear magneton. So that is, but then if you say how, so you can say it comes from the conservation of flux number. Say you have magnetic flux line. Say you have n flux tubes. So separated over a long, say you have a progenitor of neutron star, a big star. So the concept is that all those magnetic flux lines get squeezed. So the field becomes flux line per surface area that increases.
How are the spin periods decided? I mean, for neutron stars, the interval by which we are getting a pulse
Yes,
are totally determined by that.
Yes.
So, for black holes, how can we determine?
That is what I told her. We don't know. Observation we cannot.
I mean, there is no formulation of something like that.
Yeah. So for some black holes, means sweets have a companion. They accrete matter. So when matter falls to a black hole, means if it emits some photon from black hole or inside that event horizon, which is close to Schwarzschild radius, you cannot see it, right? We say that black holes even absorb photon, but if from outside event horizon there is emission of any electromagnetic wave, you can see. And in that other room there is that AGN talks are going on. AGNs are actually very massive black holes. They accrete matter and then they emit X-ray jet. But even for stellar mass black hole, say you have a black hole and a red giant star. So black hole is accreting matter and it is emitting jet. And that jet, X-ray jet can be like pulsar. So if you can measure that pulse, you can measure the spin of black hole.
Is the spin period related to the size of the neutron star?
Okay. So there is something, means we don't know the size of neutron star exactly, because neutron star said just 10 kilometers and they are so far. Like sun you can image, neutron star you cannot image that way. So that estimates I say 10 kilometers, that is from theory. But now there is effort going to...
But there are some estimates that say that the surface is extremely smooth. Like, are those completely theoretical?
Completely theoretical, and then indirect measurement, like neutron stars also can accrete matter, right? X-ray binaries. So where the matter will fall, it will give X-ray, and then accretion disk, it will give some lines, and outside neutron star there are normal matter, hydrogen and other matter. So you can get absorption or emission line. So you have a iron emission line, and then you see that line, if the neutron star spin, it gets red shift or blue shift. So those things help to find those things.
So, since the neutron stars also accrete, so do we get a jet from neutron stars as well?
Yes, you get. So that is more like black holes. They are also in X-ray. So any other question here? Okay. So, and also sometimes say you have isolated neutron star. It is not emitting accreting matter. So first you will say, okay, then why I should not be able to see it, right? Because it is already, there is no nuclear fusion. And So it is cold. Why should I do? But there is a point. It was hot, right? It had nuclear emission, so that residual heat will be emitted. Same for white dwarf also. This slide will be same for neutron star and white dwarf.
Can't we study the interiors of neutron stars using neutrinos coming out of the interior?
Yeah, so that you can do only after few for very young neutron star, because after supernova explosion you get a neutron star, and that time lots of neutrino get emitted. So and neutron stars cool, and that actually cools neutron star very fast. So from neutron star cooling curve, which is getting by neutrino, we can say things about. But again, it says something basic property, but it is very difficult to probe whether inside structure you have totally neutrons. Besides, we call neutron star, right? But there are models that not only neutrons, there will be exotic particles, say little bit. Have you heard about quarks? So neutrons are one U quark, 2d quarks, right? Protons are 2d U quark, 1d quark. But there is the other types of quark, right? Strange quark, charm quark. So there are particles we call hyperon, and which contains S quark. So there are lots of people theoretically work that inside neutron stars, especially in the core, there will be exotic particles which contains S quark. But still means we don't know which models are good. But I will come slowly means what are the ways indirectly probe what is there.
If the neutron star is radiating, then won't the angular velocity change with what is slow down?
Yes, within 2 slides I will come there. So now this residual emission would be not very high, right? But as we already mentioned that neutron stars have high magnetic field and very fast spinning, they work as pulsar. So that is we call rotation powered pulsar, and we already talked about accretion powered pulsar, right? You asked that neutron star if they accrete matter exclusively. So I will not talk much about accretion powered pulsar, and there are few neutron stars which are even extremely magnetized, say 10 to the power 15 Gauss or so. They are, if you have magnetosphere, then electrons travel along the magnetic field lines, and that is not straight, right? Curved. So curved means they have acceleration and deceleration. So Bremsstrahlung and all other effects will come. So let us first concentrate on rotation part, because they are more in number and they are studied more well. So see, inside neutron star, we say heavily magnetized, right? So you can consider you have a north pole and south pole, right? And like for Earth, you know, right? Magnetic north pole and geographical north pole is not aligned, right? Two axes. So for neutron star also it can be the spin axis and magnetic axis is misaligned, right? So neutron star is spinning, so that means that the magnetic axis is also spinning like this, right? And it is a basic theory of electrodynamics, means if electric dipole, means positive charge or negative charge, or a magnetic dipole like magnetic north pole or south pole, if it rotates, it emits electromagnetic beam from its 2 poles. So this is schematic diagram. So this is the spin axis of neutron star, and this is the magnetic axis, magnetic field lines. So neutron's magnetic axis and the magnetic dipole is spinning. So it is emitting electromagnetic radiation from its 2 poles. So say this is my emission, and say this is my Earth. So say this is rotating. My this pointer is spin axis, right? And this is your electromagnetic beam from neutron star. So if it falls, there is a, so let's say this is Earth. So if it falls on Earth, you can detect it, right? But as it is rotating, it will not be constantly on that, right? If it is rotating like this, it will go away. Again, it will come after one spin. But there are many neutron stars which might not be pointed towards Earth at all, right? It might be I have a neutron star which is rotating like this. So there are many more neutron stars in the galaxy, but we can see only the ones whose beam falls onto Earth, because it is like torchlight emission, right? And so the word pulsar is actually not right? Because when it was discovered, they thought that these stars were pulsating, so the name was pulsar. But actually, they are not pulsating; they are actually rotating or spinning. But see, this the beam of the neutron star is falling once on Earth in one rotation period, right? So from that, you can make the pulse period is the spin period, right? That is how we know spin period of neutron star. Now, Now theory is from rotation of magnetic field. It does not actually predict in which frequency of electromagnetic spectrum it will emit. So, but we study mostly in radio wavelength. The one reason was that probably you already in this school you have seen, right? Because this is the electromagnetic spectrum, and most of the part it is blocked, and the radio part we can see. And see, you can say, okay, we can see from satellite. Yes, from satellite we saw for some pulsar we saw optical or X-ray. Even if it does not, accretion is separate thing, right? But because of this rotation also, you can get X-ray. But that is fainter. Also, one thing is, when you build a telescope on Earth, you can make it very large, right? But when you want to put something on satellite, you cannot make it very large. So that is another reason that pulsars are very well studied in radio, and sometimes we simply call them radio pulsars. But that does not mean that they don't emit at all in other world. But there is two interesting points. So radio wavelength also is not a single wavelength, right? It has a large range. So from few megahertz, so 10 meter wavelengths correspond to 30 megahertz to some, I think, 5 centimeter or so. So few gigahertz, I think around 10 gigahertz. But pulsars are mostly well studied around 300 to up to 1 or 2 gigahertz. And here and this is actually a open problem, we don't know very well why. So this is the x-axis is frequency, this is in megahertz. So this is 1000 megahertz, and you see this is 300 megahertz. And you see the y-axis is energy or brightness. At higher frequency, pulsars have become faint. So that is that adds with that your X-ray satellites are smaller. Also, pulsar emission is fainter. And another, so this is one thing. And another, when we study pulsars, we have to consider that all these pulsars are far away, right? So all the signals comes through interstellar medium. So interstellar medium, it is free electrons, right? So some the photons, they might get scattered. So that is another. So we actually don't know the spectrum. I show how much is intrinsic property of neutron star, how much is caused by environment scattering and other effect. So there is lots of study going on. So we do here. You saw a different frequency GMRT plot. So this is the lowest frequency. Lowest frequency means, you know, photon energy is h nu. So nu is small, this energy of the photon is smaller, right? So it will become more affected by scattering. So you see this noise level is, this is noise and this is the pulse of same pulsar. It is not that high. So you increase frequency and you get a better and sharper peak.
And are those plots like dispersion corrected?
Yes. Otherwise, I will come to dispersion. Because otherwise, you don't see a single peak at all. It will be all scattered. So now I probably you know this is a good year, right? because this is the 50th year of pulsar discovery. So that was in 67, and by pulsar I mean radio pulsar, because first pulsar discovery was in radio. So few days ago I checked, this is the total number of pulsar, means there is a catalogue, Australian Radio Astronomy group, they publish catalogue. So there are total 2,627 pulsar, mostly isolated, some binary, and there are two triple system. One is a neutron star white dwarf in a binary, and one planet-like system around the neutron star, and another is one neutron star white dwarf binary, very short period, means close together, and another white dwarf orbiting this close binary. But only two. There are close to 280 binary pulsars, and there are different types of binaries. So, like most of the system are a neutron star, a white dwarf. Okay. So I am not keeping in time. So whenever time is over, you people tell me, huh? Because otherwise you might miss. Okay. So a neutron star, white dwarf, gravitationally bound, and they are orbiting around the common center of mass. So there are 200 such systems. There are 16 systems where there are two neutron stars, means gravitationally bound and orbiting. But interesting, only one of them is a double pulsar. Means, say pulsars are neutron stars. So from in all other cases, means this neutron star is pulsar. But when you have two neutron stars, you can say whether two are pulsars. Unfortunately, not. Means for neutron star, that 16 binary, it can be one neutron star is beaming towards Earth, right? Another neutron star can be other way. So you see only one neutron star. And I will explain how we know the nature of the company later. A neutron star black hole binary. Theory actually expect that there would be such system, but unfortunately no such system has been found yet. So when there is something called pulsar survey. We just take data from some part of the sky and we try to find whether we can discover a new pulsar. So I think all pulsar astronomers are now very greedy to discover first neutron star black hole binary. And now this is a schematic diagram, not very well. So in the very first slide, I showed the schematic diagram of evolution of star, how main sequence star become neutron star, right? And if they are in binary, how?
Ma'am, in the previous slide you said that we expect neutron star black hole binaries.
Yes.
But suppose if you have two such massive stars and one suppose forms a black hole, then it will strip the mass of the other companion, so it won't have enough mass to collapse to form the neutron star. So we shouldn't expect these binaries so much.
It comes here. So what you are saying, let me explain. So say you have two main sequence stars gravitationally bound. So the star which is more massive, it will evolve faster, right? Because more massive star, you need rate of burning higher to compensate gravity. So say you have one star, then this star say more massive than this companion. So first it becomes giant or say red supergiant. So then if they are close enough, the other will accrete matter. So okay, so accretion phase goes. Then if it still remains red supergiant, then it will go through supernova explosion and become either a neutron star or a black hole, depending upon what is the mass. So both is possible. It can be neutron star, it can be black hole. Now let us say it is a neutron star. The other is still main sequence, which accreted little bit matter from the progenitor of the neutron star, right? Now the other main sequence is evolving, so it will become a red supergiant or red giant depending upon its mass, and depending upon their separation, the neutron star can accrete matter. So if the neutron star accretes matter, what will happen? Say usually when a neutron star is born, its spin period is around in the order of second. But I said there are few neutron stars whose spin period is millisecond. That comes from here. So you have a neutron star which is spinning, and there is a main sequence star. They are both orbiting around common center of mass, right? So when the matter is infalling, matter has that orbital angular momentum, and when it falls onto neutron star, so the radius decreases, right? So to conserve angular momentum, it got transferred into neutron star. So neutron stars start rotating faster. It is just like the way you heard in the classical mechanics, right? If I start rotating and suddenly squeeze my hand, I will rotate fast. So this type of fast pulsars we either call recycle pulsar because it was slow and something happened to give it more energy, or millisecond pulsar. Now what will happen to the other? If it is a red giant without supernova, it will become a white dwarf. So you have a neutron star white dwarf binary. If it was red supergiant, and if it does not accrete that much matter, it will become either a neutron star, and if more massive, it will become a black hole. So both are possible. Means if what you are doing is good question, but if you do numerical simulation, you will see both possible because this accretion, it will not take that much mass. So you can get either a neutron star or a neutron star black hole, or again neutron star black hole can form as if this one was very massive, you get a black hole here, and that one can give you a neutron star. You can get a neutron star, black hole neutron star. So
if the neutron star is taking mass from the red supergiant and red giant, it will become slower because its mass
no. This amount of mass is negligible. You say the neutron star was born with say 1.5 solar mass. Accretion can increase its mass maximum 1.6 or something. But it is, see, the matter, say I have a blob of matter and this is my neutron star. Before falling onto neutron star, it is rotating here like there. But then when it is falling here, so it has large angular momentum, right? So it will be transported to the neutron star, and that will make neutron star faster. So,
ma'am, the Crab, Nebula pulsar and the Vela pulsars, so were they also binaries?
No, Crab, they are isolated.
Within millisecond pulsars?
Yeah, so some of them can be, but they are millisecond, but Crab is I think 33 milliseconds, right?
0.03 seconds.
0.03. Yeah. So some are born fast. So and there are many things like if it is in globular cluster, then I actually like to study globular cluster. Then it might happen you have the accretion mechanism. There are actually many more things. Means, say you got this binary and okay, let us first come to, so this is the accretion, you get millisecond pulsar. Now if this is massive energy, you have a supernova explosion, right? And depending upon the nature of supernova explosion, your binary might get disrupted or might not. So there are many isolated millisecond pulsars there are few options. First, some neutron star might born fast, depending upon when they are, so we call natal key, means when they are born, whether the supernova explosion is symmetric or not. So that will depend. But there are only, means numerical simulation expect only very few to be born fast. Then disrupted binary. It was a binary, it got recycled and it accreted matter, and then during the second supernova, the binary got disrupted. You got isolated millisecond pulsar. There can be another, say you have a binary pulsar, binary millisecond pulsar, and if it is in a crowded field, there are lots of stars, which happens more likely to happen in globular cluster or close to the galactic center. Another star can come and disrupt the system. So for all isolated millisecond pulses, we don't know which one came from which channel. But this is not ruled out.
What is the probability that such a system will evolve into a neutron star and a black hole? Like whatever you explained, it will start with two massive stars.
Yes.
What is the probability that the end product will be a neutron star and a black hole?
Yeah. So present simulation, it's a belief that means if you have, see, all things means probability, right? So the fraction of neutron star black hole and neutron star is 50:1. So still we have only 16. So statistically, yeah, they can exist, and we are just not statistically enough number of stars. But again, the statistics depends on lots of your model parameter, means different types of stellar metallicity and everything. But the most commonly believed is 50:1.
Well, in the previous slide, the triple system, that one is neutron star, white dwarf, and planet. But planetary formation is completely different from this process. So, from a massive star, can a planet form?
White dwarf progenitor was not that massive, right? And also, Miss, I don't think anybody ever studied. This is observationally we found, but yes, you are right. For this planet, its formation is different than the planets we see around our sun or those normal exoplanets. But interesting, these days we talk too much about exoplanet, but this was the first exoplanet. But as it is totally different than normal planets we are talking about, exoplanet people don't mention about that. But this was the first exoplanet. I think it was, I don't remember, it was sometime 96 or sometimes it was this one.
So this planet was not formed from this white dwarf. It might have been captured from some other system.
It is also possible, but it is not possible to say. But one thing, it might not be very likely what you are saying, because this is not in a very crowded. If it was a globular cluster, it would be okay. But we don't know how it was formed.
We say that when the planetary nebula is found around white dwarfs, maybe from that the dust accumulated.
Yeah, it is quite likely, but it is very difficult to just pinpoint the formations, and because there are so many possibilities. Any other?
So was this planet created using the light curve of the white dwarf?
No. For the I will come to timing analysis. So because these pulsars are very accurate, means so their timing is very accurate. So first, from seeing the timing, you can say it is a binary neutron star white dwarf. Then you keep on timing. Then you say that okay, something is wrong. Means I cannot model it. So you need put a planet. And this one was also very interesting, because the where I was that time doing my postdoc there in West Virginia University, one student was, he actually discovered the neutron star white dwarf system. So he was doing timing analysis. So after some times I remember he was complaining a lot that this system, something is wrong, I cannot model, my timing analysis is not working. And he was becoming 50 years. So then he said, no, something is wrong, I don't want to work with this system because I need to finish my thesis. So he stopped working on that, and he submitted his thesis and went. But then his supervisor and others, they tried to figure out what is wrong. Then they realized, okay, if we add another white dwarf, then it fits the data. So that is one thing. It's never, if you find something problematic is happening, probably you are going to discover something new, right?
Ma'am, the that can be a smaller mass main sequence star also, right? Why? A very small mass main sequence star.
No, because the mass will give you, change the gravity, right? And that will change your gravitational model. I will give some brief introduction of pulsar timing also, that will be more clear. So, any other? Okay. So I think we have mentioned already as, so few small points, as pulsars are actually very faint. So far all the radio telescope we have been able to detect pulses only in our galaxy. Means extragalactic pulses means we have few in large and small Magellanic Cloud, but not in other galaxies. Probably you heard of SK, right, in your school, Square Kilometer Array. So we are hoping when SK will come, probably get pulsars in other galaxies, because in other galaxies there are stars, massive stars, so there should be pulsars there also, right? And as just now I said, pulsars are faint. So most of the pulsars, you know Jansky, right? Because you are having radio astronomy school. Jansky is the unit of flux for radio astronomer, 10 to the power minus 26 joule per meter square per hertz. And pulsar flux, you see that in 400 megahertz, mostly less than 100 millijansky. It is not even Jansky. Most of the pulsars are in millijansky. And as I showed you that spectrum, so pulsar spectrum, it is the spectral law. If you increase frequency, your flux density decreases. And she is Jocelyn Bell, who discovered, it was her PhD, part of her PhD thesis, discovery of pulsar. And here I saw few radio telescopes. It's large. This is Parkes in Australia. This is Arecibo. It is 300 meter diameter, too big. So, have you seen those movies? I think few movies Arecibo came. I think one was Contact, yeah, and then I think some James Bond movie also was there. Okay, so I have not seen that movie, but see, it was, you cannot imagine, because before seeing it, I knew, okay, 300 meter, but when I saw, oh my God, so big, and actually it is very interesting, because it is so big, they don't, you cannot move it, only there is that feed with the detector, you move only that one, you don't move the telescope. And this is in Puerto Rico, and this is in Great Bank, again in US. So this is the largest steerable telescope, 100 meter diameter. That is also big. 100 meter is not small, right? This is Effelsberg in Germany, and this is GMRT. So GMRT is something innovative, because when it was built, they realized that making big dish is very problematic, and sometimes to make nice image, for pulsar dishes are better, but for other type of things, if you want to make pretty image, interferometer is good. So they made how many? 30 antennas, but you can add all antennas together and use it as a dish. So GMRT is also being used for pulsar, and I think you people have some GMRT trip, right? And so I will actually be, tomorrow I'm going to GMRT, so we are doing a survey of pulsar. So we are trying to find whether, because GMRT have been recently upgraded, so we expect it to be more sensitive. So we are trying to see whether we can discover new pulsar with GMRT. Now, see, you record a signal from a pulsar. Now, how you say, okay, this is from a pulsar, not from some crazy object. See, sun also emits radio, right? So then it can be a GM. So there are few things. First, yes, if it is pulsar, it should be periodic signal. And we know from theory, periodicity can be between millisecond or second. If I see something in hour, I'll say, okay, this is something else, not neutron star, not pulsar, which I am interested. Then something RFI or human-made signals. So in GMRT, for that purpose, your mobile phones are not allowed. When you enter, they will say switch off your phone, because phone, digital TV, and few of the satellites, we are having lots of problem with some US military satellite, because they all emit electromagnetic wave, and few things are periodic, right? Like our AC power line, that is AC, periodic. But human-made signals are usually either you say I want a signal with this spin frequency or with this spin frequency. So that is close to integer number, right? But nobody asks the pulsars to rotate in an integral period, right? So when you see some period, but this is not a very hard and fast rule. But when you see some signal for which either period or frequency, means inverse of period is the integer, then we become suspicious. Then broadband. I already showed, right, that pulsar spectrum throughout. And human-made signal, you know that all these TV channels and cell phone, they have their designated bandwidth, right? They cannot emit. So that also one thing you should check, whether it is wideband or narrowband. Here I show some plot. This is a real pulsar for plot. There's two pulses. So x-axis is time, y-axis is frequency. So there are many frequencies. One frequency is frequency of radio wave, right? And another is spin frequency. So here it is the frequency at which we are observing. So sometimes I say I observe at 1.4 megahertz. I observe at 300 megahertz. But again, your telescope has some bandwidth. So GMRT earlier had 30 megahertz bandwidth in each central frequency. Now we are trying to observe in 200 megahertz bandwidth. So this is not GMRT, this is some, I think, Effelsberg, around 200 megahertz. So you pulsar data, and this is the signal, means color code is signal. You see that black is throughout the band. And this is the same system, but RFI, means radio frequency interference. You see only a small band. So this is how we identify. And another is non-zero DM, dispersion measure. So you know about dispersion measure in the school? Okay. So I think there are different types of logging, so I don't know. So C means, we know that speed of light in vacuum is constant c, right? But when light travels in medium, especially ionized medium, it travels with its group velocity, right? And this is the equation for group velocity. And this Fp is the plasma frequency, and F is the frequency of the photon. And plasma frequency, if it is, I am considering that interstellar medium, which is actually very diffuse charge electron. So E is electron charge, number density of electron, mass of electron. So that means here you have F, means frequency of the photon. So different frequency photon is traveling at different speed, right? And as I already said that your telescope is covering a wide range of frequency, right? So same pulsars are far away, few kpc. So same photon, it started from the pulsar same time, but it is reaching Earth at different frequency at different time, right? So this is not very clear. So this is over an entire bandwidth. So some and this is time. So some photons reach earlier, some in other. So see, your telescope has wide bandwidth, and different band has small channel. We call channel. So each channel records your signal. So in different channels, different frequency, you get the pulse at different times. So then pulses are already faint. You cannot see them. But if they would arrive at the same time, then you can add the signal in all channel and you get a bright pulse. So this is called dispersion, means this time. So this is the group velocity. So time takes to travel is distance by group velocity, right? And the delta t is the time difference between two frequencies. So you take frequencies and this is square, and then electron density I keep inside this integration, because electron density in our galaxy is not constant, and it actually depends in different direction. So the whole thing together is called dispersion measure. So to observe pulsar, you need to follow a procedure. I think you will learn in your tutorial, D-dispersion. So when it is unknown pulsar, it is very difficult. You say, okay, probably this delay is say something, I give a guess value, and for each consecutive channel, I give a guess value of shift and I try to align. So for which guess value I get a very good alignment and best signal, that is my dispersion measure. And when you have already a known pulsar, you are re-observing, say you want to study some other property. Someone discovered the pulsar and told you the dispersion measure. You know that becomes much easier. But for pulsars, there should be non-zero dispersion measure, right? Because it is coming. It is at least covering, even if it is very close, some ISM it is traveling through. But say mobile phone, that is coming just from next door, right? So you will get a signal with no dispersion delay. So that is another way to get rid of a human weight thing. Now, I think I should go a little faster. So what do I do? Let's say we are observing a pulsar. So a pulse is coming, I am recording pulse. So I record 1 pulse, 2 pulse, 3 pulse. Say I have 10 pulse. And if I see, I think someone said that why pulsars don't get slowed down. They actually get, because pulsars are emitting radiation, right? And radiation is energy. Where this energy is coming from? It's rotational kinetic energy. So there is a P dot. So you know P and P dot. But there are few other things. Because, like as I already said, pulsars are far away, and some of them are also moving, because when they are born during supernova explosion, they got some kick velocity. So, see, spin period would be the same as I have 1 pulsar with spin period 1 second. So it is emitting pulses at 1 second interval. But when I am observing, that depends on the distance, right? Say t plus d by c. But if d is changing, so pulses will not arrive at the same. So we need to model the Earth's motion around the sun, and if the pulsar is binary, pulsar's motion, and if it has proper motion, means motion due to its heat. But if we do all the modelings, then what do we? That is what we call timing. So you have 10 pulses. You measure the arrival time. So from that you got spin period derivative. Then you are confident your model is good. You can predict when next 10 pulse will come, right? Then you wait. When next 10 pulse come, you match your prediction with your observation. And if you see there is slight deviation, you go to the loop and you refine your parameter. And this I show you, this is called timing, a residual. Means if your model is good, your predicted time and observed time, the difference would be close to 0. So this is the 0 and this is close. And these are some when the model is not good. So here, if there is P dot, if you did not model P dot, so pulse period difference will increase. This is if you model pulsar location badly, so it will come in the Earth's motion, right? And that is periodic. So it is actually 365 periodic. Now this figure means here all known pulsar. This is P0 is spin period and P1 is spin period derivative. So this is called PP dot diagram, and that is actually very important. That say lots of things about pulsar. One thing what I already say, that rotational kinetic energy half I omega square, right? Omega is angular speed, I moment of inertia. So E dot, moment of inertia is property of neutron star fixed. So then it will be omega dot 2 will go away. And as it is losing energy, I put the minus sign, right? And then as it is, I said that emission is because of rotating magnetic dipole. So this is the theory of electromagnetic radiation. Means if you have studied electrodynamics, the E dot of dipole radiation, this has this bond. This M is dipole moment, this is B magnetic field into radius cubed, and this psi square alpha is the angle between spin axis and the magnetic axis. So you equate these two, and then instead of M you put VSR cube. So you get this expression. And theoretically, we already know that moment of inertia of neutron star should be 10 to the power 45, and you know that in astronomy we prefer CJ system over SI. So moment of inertia we know roughly, we know radius around 10 kilometer, and this value, because value of the alpha means inclination we don't know. So this is the maximum value, means when we took sine square alpha is 1. So you get this. This is how we, and P dot you measure from your observation. So this is how we can give some estimate of magnetic field. And similarly, again from when you equate to this omega is 2 pi by P, right? So you get some P dot equal to some, this is the constant, means M, P dot is that constant by P. So you can integrate, and so from 0 to T, T is the age of this. So you get that constant into age. This, say P0 was the initial spin period and P is the present spin period, you get it. And if you say, okay, if P0 was much smaller, you can neglect and you get some rough idea about the age. So, but that is characteristic, that is not real age, right? Because nobody said that P0 should be negligible. So that is how in PP diagram you will see those lines 10 to the power 9 Gauss, 10 to the power 10 Gauss, 10 to the power 12, 14, and those are lines of constant age. So this gives you a rough idea about which pulsar is, how much magnetic field, how old it is. These are the millisecond pulsars. Okay, now I think this was, I thought I would keep one slide about accreting pulsar, but I think we have already talked about it, right? That accretion, it falls onto the near magnetic pole and you get X-ray. But there is another, recently people are studying a lot pulsars in gamma ray. So there is that NASA's Fermi satellite. With that few, I think now around 200 pulsars with gamma ray is known. So those are the few known gamma ray pulsars. And the emission mechanism of gamma ray pulsar is, gamma ray photons is not very well known. There are lots of theories, some theoretical model that okay, there is electrons, they get accelerated in high magnetic field, and then they give gamma ray photon, and then each photon breaks into electron positron, and you get more a shower like thing. So I'm not going into details because it will take one day itself. Now, as I say that you observe pulses, and so far I said okay, to get pulse period and P dot, you need Earth's motion and all other things. But if you pulsar is a binary, then pulsar is moving in its orbit, right? Because of that, the distance between the pulsar and Earth is changing, right? So by doing timing analysis, you get the property of orbital property of pulsar, like eccentricity of the orbit, orbital period, semi-major axis, and but there is one interesting thing. See, say this is you are the Earth, and this my hand is the orbital period, right? The distance will depend upon how the orbit is inclined to you, right? Means you have an orbit like this, orbit like this, orbit like this. Means along your line of sight, the distance is what is smaller. That is why we cannot determine the true semi-major axis. Means semi-major axis projected along, means I is the angle between sky plane and orbit, so sin I, and omega is called longitude of periastron. So we talked about this direction, right? But again, when you have an eccentric object, whether it is like this or like this, that will also come, right? So how it is oriented in this plane, that gives you omega. So this is if your pulsars were just classical system. If only classical mechanics, you got this. So when you start timing, first you get all these parameters. Then because neutron stars are compact object and they have another companion white dwarf or another neutron star, they are also compact object. GR effects come. And general relativistic effects means full general relativistic, doing all tensor calculus. It it is very difficult to incorporate in your timing analysis code. So we do something which is called post-Newtonian approximation. It's like we know that you need to do tensor algebra and all these things, but some simplified thing which gives you some more parameter in your timing analysis code. One is omega. I will mention omega dot. Means how this orientation, how it changes. Then PB dot, rate of change of orbital period, things called Einstein delay and Shapiro delay. So one is periastron advancer omega dot. That has been actually first measured in our solar system. This Mercury's orbit, it precedes. If you had classical system, your objects are moving like. But due to general relativity, it also orbit also precedes. So that is one. Another is decay of orbital period, and I think now you all heard about LIGO and all this thing, right? So, like electromagnetic wave is taking its energy from rotational kinetic energy. You have two neutron star, white dot. They are emitting gravitational wave, and that gravitational wave also carrying energy, and that energy is coming from orbital energy. So the orbit shrinks. So that there is that decay of orbital period. So the first binary pulsar, when it was discovered, PB dot was discovered. So that was first indirect proof of gravitational wave. So that was by Hull-Stellar. We call it Hull-Stellar binary. And then Shapiro delay. Shapiro delay is actually the effect of space-time curvature. So it will be clear from this diagram. Say this is my pulsar, this is my companion white dot. Just I took it white dot. So this is the orbital phase. So you know, GR says that if you have a massive object, it curves space. So say this is my pulsar, this is white dot, and you are people on Earth. So if the pulse is coming towards you, when it comes, if it was isolated pulsar, the pulse will travel a flat space, straight path. But as there is white dwarf, when the pulse is coming very close to the white dwarf, it is traveling to curved path, right? It travels to extra path. And so that, but that will depend on two things, mass and orbital inclination. Because for mass is very clear, right? More massive, more curvature, more deviation. And inclination, I am saying like this, but if you have an orbital system like this, white dwarf and neutron star moving around this, so then your pulse is coming towards you. It is not coming very close to the white dwarf, right? So this Shapiro delay will not be. So that is why there are two parameters related to Shapiro delay. Shapiro shape, which depends on inclination angle, and Shapiro range, which depends on the mass of the number. Then Einstein delay, that is the time dilation because pulsars are moving, special relativistic, and change Doppler shift coming as because of the motion. And this is one slide with some equation. So from this, our knowledge of GR and post-Keplerian approximation, you can write all this Keplerian, post-Keplerian parameter, I said omega dot, PB dot, you can derive the expressions. And those expressions, this T sun is just a constant G m sun by sigma. So this expression depends upon Keplerian parameter like orbital eccentricity, MP is pulsar mass, and MC is component. So you have done timing analysis. You know orbital period PB and eccentricity, and you know this right hand side omega dot gamma. So you have one equation, 2, 3, 4, 5 equation. This Fe comes here, that very complicated expression of it. So you have 5 equations and only 2 unknown, mass of the pulsar, mass of the component. So you can solve. That is how we measure mass of the pulsar, and companion also comes here. So here you see this is radius and this is mass, and you see lots of lines. We call mass radius diagram. Those lines are theoretical prediction of mass radius. Same and different equation of state. Equation of state means what you believe as what in the beginning we are talking about in interior structure. whether it contains hyperion or not, what types of nuclear force those particles exist. So say, let us take one AP4, this line. So how you interpret this line? Say, if I believe in this line, I will say, okay, if I have a pulsar of neutron star of mass 2 solar mass, y-axis is mass, x-axis is radius. 2 solar mass, its radius will be 11.5. But if I have a neutron star of 1 solar mass, its radius will be larger, close to 12 solar mass. So now, from the timing, we show that how we get mass. So these red lines are some of the measured, some examples. So you see, this is the heaviest pulsar we know. It actually excluded some equation of state, means which cannot give maximum mass up to 2 solar mass. But still lots of equation of states are available. So I don't get time to include, but recently that LIGO people, I think you will have a talk on that. They studied the Mars. They had, So I said that 2 neutron star, they are spiraling emitting gravitational wave, you get PV dot. But still they are far apart. But eventually they will come close together and merge. So during that merger, depending upon equation of state, how they can totally deform each other. So that those LIGO people have studied, and they actually excluded some of those equation of state. So I don't have that information here. That was very recently. But still there is a wide range of equation of state available. Another might be if you can measure moment of inertia, which should depend upon mass and radius, but not Newtonian. Means in GR calculation it will depend on speed also. But once it's spin we know. So there is effort to do measure moment of inertia and pinpoint the radius. So those two was the details how we can do. I'll exclude. Now what we are saying, say you have a binary pulsar. You know mass of the pulsar and mass of the component. But who said that component is a neutron star or white dwarf? Actually we do, people do optical or infrared or ultraviolet observation, because we know if it was another neutron star, it would not emit, right? But if it was another white dwarf or main sequence, how would the companion do? So this is actually the image of the triple pulsar. I said neutron star, white dwarf. This is the one white dwarf component, and this is the another white dwarf. I think this is the ultraviolet image. And from that, they could actually say that both the components are white dwarf and what are their composition and temperature. This is the triple system. I think I mentioned that. How about that student? He was finding something he could not model, then it was realized it was a triple system. Similarly, means if you are find something you cannot model it, you are not getting good timing, solid state is not coming to 0. There might be something new is coming. So that new can even be low frequency gravitational wave. So let me briefly mention, see, you have heard about gravitational wave and LIGO. But there can be gravitational wave created by different things. Like LIGO is actually very high frequency gravitational wave being created by merger of neutron star or stellar mass black hole. Theoretically, a neutron star black hole merger also possible. Then there is a plan to put some interferometer in space, LISA, which will observe slightly lower frequency gravitational wave. But there are very low frequency gravitational wave, and the more massive the source, the frequency becomes lower. That actually you can get if you do the full GR calculation. So say, as we know that at the center of each galaxy there are supermassive black holes, and there are merger of galaxies. So there you get a gravitational wave of nanohertz frequency. But how can we detect them? Because to detect them, actually you need very large interferometer. Means it's not even hundreds of kilometers. Huh? So the one thing presently we are trying to do few groups of means we don't build interferometer at all. Because we have lots of pulsars in the sky. They are all in our galaxy, right? And say in far away, two galaxies have been merged. So the gravitational wave is coming from. So when the gravitational wave passes through our pulsar, what you expect their pulsation to arrive, there will be some change. So by doing that, you can detect gravitational wave. But so that is called pulsar timing array. Means there you have an array of pulsar, means not array of telescopes. When I was a student first time, I got confused. So array of pulsar, you time them well. When you see something is different is happening, then you check whether means what we predict with the background gravitational wave. So basically few groups are working. One is Australian group, one is European group, and one is North American group, means US and Canada. And for last 2 years, we are also working. Means we have started a group with NCRA people to do timing. So let us see what happens.
Only the pulsar radiation only will be distorted by the. How can we say that only will be distorted by the GW wave?
No. Pulsar emission will not be distorted. It will be the like LIGO, means when the gravitational wave came, the length of the interferometer change. Here also, when the gravitational wave come, the distance between the pulsar and Earth will change little bit. So that will shift your pulse arrival time, right? And why you have array of pulsar? Because see, my source is in this direction, so it will change the pulsar which is along this direction. In some other direction, there will be some cos theta factor. So in that way, you can even localize the pulsar. It will not deform pulsar signal. It will just change the distance between the pulsar and the. And this is, I hope I did not take long. Right? So why pulsar astronomy is would be very exciting for if you decide to become pulsar astronomer, because lots of amazing instruments are coming. I mentioned about upgradation of GMRT, that you will know more. But there will be something called square kilometer array. So it will be means array of telescope square kilometer, means kilometer by kilometer, and will be in different frequencies. So low frequency array, mid frequency, and high frequency. So high frequency will be in Australia and two other in South Africa, because those two are, you get very nice empty desert region, no human disturbance. But still it will be in these two countries. But most of the world, means all this dark blue region, are participating. So India is also a part of square kilometer array. So you will get opportunity to use the data and use the facility. So lots of things will be happening, and I hope for it. Say pulsar in Andromeda or some other galaxy. Okay. So any question here? Nice question.
We're taking that the binary NSNS pulsars.
Binary?
NSNS pulsars, NSNS or NSNS. The direction of emission is different. I mean, we are receiving the data from just one NSNS.
Yeah, so but there is one NSNS system which is called double pulsar, where luckily both the pulsars are emitting us. So we call pulsar A, pulsar B, because you know how we name any astronomical the right ascension and declination, right? We give the name. So that pulsar is J0737 minus 3039. But they are very complex. You cannot in RD you cannot differentiate. So we call them J0737 minus 3039 A and B. So A is the first second pulsar which born first, and another is slow pulsar 27, that is the born.
I mean, in this combined system, both are participating elements we receive the emission from both.
Yeah, so both are actually there is, but both are emitting towards part. You know about geodetic precision, right? So say you have the spin, and say this is the magnetic axis. So magnetic axis, we say this is the alpha angle, right? when the pulsar is spinning, this is also spinning. But then there is something called geodetic precision. This angle alpha, that actually changes. So that change. So at present, double pulsar is not a double pulsar for last 3 years. But models predict it will be back in 2022. Means it will make one rotation that magnetic axis and the beam will be again pointing towards.
So the pulsars have a very high precision then.
Yes, this pulsar has very high precision.
Is it because of the high magnetic field?
No, it is because in a short period, because it is gravitational precision, not magnetic precision.
So what determines the precision radius? Both the mass or?
Okay, I can show you. I can actually show you. Just. Last week I was there in a SK conference. Show you talk from that. Few things are same. You can see all the things. So this is some image, some X-ray binary, and this is a kind of. I forgot to mention. This is actually another type of binary pulsars. Very interesting. So you have to know sun has strong solar wind. Pulsars also have pulsar wind. And for few systems where the mass of the companion is not that high, but it was very close. So because of pulsar wind, the companion is getting destroyed. And so the companions are very low mass. There are, we call them spider, name of after black widow pulsar. Yeah, it depends on the mass and few other things. Okay, if you don't mind, I can show you. So I was recently studying that. Just we are